Hey guys, this is the first video for Unit 10, which is on gas laws. Today we're going to be talking about Avogadro's law. So let's jump right in. We're going to be on page number 3 in your packet. So we've talked about Avogadro before. He's the guy who came up with the mole. So if you remember right what a mole is, you should know by now. Kind of going along the same lines where if we've had the mole roadmap in the past where we had mole, in the middle, and we had like mass over here, and we should know how to kind of go back and forth. And let's say we had particles over here, okay, where we kind of related all those together. And then there's actually a third route we could go, and that's dealing with volume. And I specifically wait to do that until we get to gas laws. And that's right here. So we'll talk more about the conversion factor that is related to volume later on in this unit. But for now, that's kind of where his law comes out of. And what he says is gases, so this is only for gases, at the same temperature, pressure, and volume all have the same number of molecules or particles. Okay, so it doesn't matter what gases you have, if they're at the same temperature, pressure, and volume, they're going to have the same number of particles. Okay, now that doesn't mean that their masses aren't going to be different, because we know that each substance has a different molecular mass, but we're talking about just the number of particles here. That's why, again, using this roadmap right here, that when we have volume or something like that, we need to go back and see, well, how many moles there are. Okay, because volume, particles, and mass, they can change. Okay, but particles here, if the volume is the same, if the temperature and if the pressure are, they're going to have the same number of particles. That's what his law shows. So if we take a look here at these three boxes, we should be able to answer these three questions based on that. Okay, and we'll kind of explain why the answer is the way it is here in this video. So which one has more particles? Well, we just said that they're going to be the same. Why? Because according to his law, because they are all at the same pressure, volume, and temperature. Okay, so just keep that in mind, that if they're all the same, they're going to have the same number of particles. Now, which one behave most ideally? That is going back to our last unit. So ask yourself, well, what are the conditions where gases act most ideal? Remember, they need to meet the 5 assumptions of KMT, so they got to be moving fast, they got to be far apart, no collisions, or excuse me, no elastic collisions, so they're not losing energy. So basically, we want them spread out as far as possible, and we want them moving as fast as possible. So highest temperature, lowest pressure is going to make them most ideal. Well, when we take a look at that, we notice, oh, they're all moving, they are all at a high temperature, so they're all moving really fast, and their pressures are all the same. So we can't just look at those two things. So if you think back again to last unit, what else helps them be most ideal? There's another factor that comes into play. Can you think of it? Mass, right? So we talked how, we had that problem where if ammonia gas and chlorine gas were released, which one would reach the back of the room first and move the fastest? The one with the least amount of mass. So the lower the mass of a particle, guys, the most ideal it will be, because they'll be moving a little bit faster because there's not as much mass. So if we look here and look at the molar mass of carbon dioxide is about 44 grams per mole. Hydrogen is about 2, and argon, if I remember off the top of my head, which I don't have my reference table in front of me, I believe argon is like neon's 20. I think it's like around 40. No, it's not around 40, but it's more. Hydrogen here is going to be our guy that acts most ideal. So hydrogen, and be able to explain. Okay, so if it asks to explain, you got to make sure you explain it, because it's the lightest and therefore will move fastest. And it'll also have the least forces between the particles. Again, that goes to the mass, right? Bigger the mass, the more force it has between them. So now, question number 3, and this is a common question too, which one has the most atoms? So you might think, well, they're all the same. Guys, are all atoms the same? Are they the same as a molecule? No, right? A molecule means there's bonding taking place. So we can look and see how many atoms each one has. So if we take a look, we've got up here, we've got carbon dioxide. Okay, we've got hydrogen gas, which is a diatomic, and we've got argon. Well, count up how many atoms they have. Well, let's see, we've got 1 carbon atom and 2 oxygen. So therefore we have 3 atoms here. Hydrogen has got 2 hydrogen atoms bonded to each other, diatomic, and then argon just has 1 atom. Okay, when everything else is the same. So the same number of particles in their sample because everything else is held true, but when we break it down into individual atoms, if I were to draw these structures out, we've got carbon dioxide, and you can see the 3 individual atoms. Hydrogen here looks like this, and then argon. So if you go through and count them, so again, make sure you answer the question that's asked, okay? This is a question you could be asked on the Regents, so make sure you're aware of it. So slow down and make sure you know what it is. So I know this isn't, traditional notes here or anything like that, but go ahead, use this information, this hypothesis, or excuse me, this law of Avogadro's to do your best to answer these questions. Now, this may be challenging, some of them, so you may have to, really think outside the box, but ask questions, do some research, and you guys should be good with this. Now, I will point out number 8 and number 9 we're going to have to come back to. Okay, you'll have to. The easiest way to answer those is to use a law, or excuse me, a formula that we're going to get later on in this unit. So you can try and do it now, but you may not be able to understand it fully until we come back with that formula. All right, until next time, I'll see you later.